Today we're going to go over section 4.2, solving linear systems by graphing, substitution, and elimination. We know a system of linear equations in two variables x and y consists of two equations in the forms of ax plus by equals c and dx plus ey equals f, where all of those are basically integers a, b, c, d, e, and f. So remember that standard form from last chapter. The solution of a system of linear equations in two variables is an ordered pair, x, y, that satisfies each equation. In other words, when we plug them into both equations, we'll get true statements. When the system of equations is graphed, there should be two lines and they should intersect at a point, which is called the solution. If the lines do not intersect, then no solution exists. This would happen when the lines are parallel. If the equations are both the same line when graphed, then we can say there's infinitely many solutions because the line intersects everywhere, so the solution technically would be the equation of the line. So in number 1, we want to graph the line and determine the solution. So we're going to graph each line of the system. So we're going to graph y equals 3x. So remember that would have a y-intercept of 0. I'll turn on my pen. And we'd have a slope of 3. So we go up 1, 2, 3, and over 1. And we can graph this point. And we're probably, for sake of graphing, we should go down 3 and left 1, down 3 and left 1, and draw the best line that we can. Now we're also going to graph x plus 2y equals negative 14. I prefer to go ahead and put this in slope-intercept form and divide by 2 so that we know our slope is negative 1/2 and our y-intercept is going to be negative 7. Okay, so we go to negative 7. Go down 1, right 2. We can see that it's going to intersect actually to the left in the third quadrant, so we'll go up 1, left 2. Draw our line. And our solution will be where they intersect. And that solution is negative 2. Oops, sorry. It's negative 2, negative 6. Okay, moving on. The system above is an example of consistent equations, which yield one solution. Algebraically, we learned two other methods. We're going to basically quickly review these methods. You should have learned this in Algebra 1. Hopefully you remember the word substitution. The other method was linear combination, but some teachers prefer to call it elimination. So, substitution. We want to take the one that's solved for y and substitute in the other equation. So we're going to write 2x plus 1/2 x minus 4 equals 6. We're going to go ahead and combine like terms. We get 5 over 2x equals 10. We're going to multiply using chapter 1's multiplicative inverse. We're going to multiply by 2/5. And we're going to get x equals 4. Now to find y, we can go back up to the first equation, plug in x, 1/2 times 4 minus 4, and we get negative 2. So our solution to this problem is always an ordered pair of 4, negative 2. Elimination. Remember when we do elimination, we're going to add the columns. So we have to either decide to get rid of the x's or get rid of the y's. I'm going to go ahead and get rid of the x's. So I'm going to multiply. Sorry about that. So I'm going to go ahead and multiply the top equation by a 4 and the bottom equation by a 6. So when I do that, the top equation I get 24x minus 8y equals negative 16. On the bottom I get negative 24x plus 18y equals negative 24. So now I add the columns, and we get 10y equals negative 40. So y is negative 4. Then to find x, I want to substitute. I'm going to use the top equation, 6x minus 2 times y, which is negative 4, equals negative 4. So I get 6x plus 8 equals negative 4. Subtract the 8, I get 6x equals negative 12. So x equals negative 2. So my solution is negative 2, negative 4. Okay, moving on to the back page. Solve the following by your choice. I would say if it's not isolated, I would go ahead and solve by elimination. So I'm going to multiply the top equation by 2. That's going to give me a 2x minus a 6y equals negative 10. Add the columns. Uh-oh. Everything dropped out. When that happens, basically we know we have the same line. So the solution of this problem is the line x minus 3y equals negative 5. We would say there's infinitely many solutions. But the actual solution for our answers on a test would be the line x minus 3y equals negative 5. Because basically, these two lines right here are the same. So they lay on top of each other, so therefore any coordinate on that line will satisfy both equations. Alright, look at the second problem. I'm going to multiply the top by 2 again, and I get negative 2x plus 2y equals 12. And now I'm going to add, and I'm going to get 0 equals 16. Well, that doesn't make any sense. 0 does not equal 16. So because that doesn't make sense, these lines must be parallel. So we actually have parallel lines. So there is no solution. Alright, moving on. Number 5, the one with the line, is an example of a dependent. Actually, keep that straight. We'll match the color. That example is an example of dependent equations which yield infinite solutions, whereas number 6 is an example of inconsistent. So you got some vocabulary words to learn. You got consistent versus inconsistent. Basically, consistent means there is a solution, inconsistent means there is not. And then you've got independent scenarios or independent scenarios. The dependent one is really the thing that where they have the same line. It kind of depends on the line, and it depends on what you choose for the point. But as long as it's on that line, it's a solution. So questions like 7 can come up. Determine if 0, 2 is actually a solution. So if we plug in 0 for x and 2 for y, we want to see if that yields 16. So that is 16 equals 16. So that's check. But it's not enough just to do one equation. Remember, a solution is an intersection. An intersection. Okay? So that means it has to work on both equations of the lines. So negative x, if we plug in 0 for that, and 2 for y, down below we get negative 8. That is not equal to 8. So that's a no. So therefore we'd say no, this is not a solution. Finally, we've got your school, a word problem. Your school is planning a 5-hour outing at the community park. The park rents bicycles for $8 per hour and inline skates for $6 per hour. The total budget per person is $34. How many hours should students spend doing the activities? So when you have systems of equations, you have to figure out the two variables. And there's a lot going on in this problem. But the variables are actually the number of bikes and the number of skates. So we're going to let x equal the number of bikes, and we'll let y equal the number of skates. So now we have to set up two equations. So the first equation is we know that we have a 5-hour outing. And we have how many hours should the student spend doing each activity. So there's some key words in here. So we know that x plus y has to equal 5. Other options that we have is we have this money, $8 per hour, $6 per hour, and $34. So those, obviously money relates to money. So 8x plus 6y should equal 34. And so now we can go ahead and figure out what we want to multiply by. And I would multiply the top by negative 8. So that's going to give me negative 8x minus 8y equals negative 40. And we can add these problems. So we get negative 2y equals negative 6. Y is 3. So now if we go back up to this red equation, x plus y equals 5, so now we know that x must equal 2. So we have 2, 3, which basically means we have 2 bikes and 3 skate. And these are actually, I kind of misspoke. The number of bike hours, I left that off, the number of bike hours, and the number of skate hours. So these are 2 bike hours and 3 skate hours, because remember, the total hours was 5. All right, I think you have enough to help you with your homework. Good luck.